Breaking news. The interstellar comet 3I/, discovered on July 1st, 2025, is defying the laws of orbital mechanics. Instead of simply accelerating toward the sun, it has begun a bizarre pattern of speeding up and slowing down with pulses every 17 minutes, as if ticking like a cosmic clock. Telescopes from Hawaii to Chile confirm the anomaly. Is it natural? Jets of CO2 bursting from its frozen surface? Or something far stranger, a relic older than Earth, a molecular vault from 7 billion years ago, is now sending shock waves through astronomy? What exactly is passing by us? The strange motion. On July 20th, 2025, telescopes in Chile and Hawaii reported something unusual. The interstellar comet 3I/ was not behaving like a simple rock obeying gravity. Normally, an object entering the solar system follows a predictable curve: acceleration as it falls toward the sun, deceleration as it moves away. But measurements show irregularities. At 200 hours UTC, its speed increased by about 8 meters per second more than models predicted, then dropped slightly over the next 36 hours. This wasn't noise. Careful checks by the European Southern Observatory confirmed the anomaly on July 22nd, noting a measurable non-gravitational acceleration. The effect was tiny compared to gravity, roughly 10 theus 7 astronomical units per day squared, but persistent. Astronomers compared it to the strange acceleration of Oumuamua in 2017, but stronger and more erratic. Instead of a smooth curve, 3I/L seemed to twitch forward and hold back. Even at 1.2 astronomical units from the sun, when gravity dominates, the deviations could not be ignored. By late July 2025, the pattern deepened. Observers in Spain, Japan, and Arizona confirmed alternating phases of acceleration and slowing. Each phase lasted about 17 minutes, echoing brightness pulses already noticed in its coma. These weren't random jets. The intervals repeated with uncanny regularity. For comet physicists, it was maddening. Outgassing could cause thrust, but why would it act like a clock? If natural, the vents must open and close in cycles. If artificial, the implications were extraordinary. NASA's Jet Propulsion Laboratory issued a cautious note on July 28th, acknowledging non-gravitational perturbations. They compared them to thrust from CO2 and H2O sublimations seen in other comets. But privately, some researchers admitted the scale didn't match. Even with heavy carbon dioxide release, the forces required to alter a 30 to 40 kilometers nucleus by such amounts seemed excessive. The mystery grew. Was 3/ATL a comet at all, or a relic with unknown physical processes at work? The strange motion of 3/A was more than a curiosity. For the first time, astronomers could watch an interstellar visitor accelerate and slow in ways our models could not fully explain. By the end of July 2025, the evidence was undeniable. This object was not simply coasting under gravity. Something else was pushing and pulling it. To uncover the cause, scientists turned to spectroscopy, scanning its coma for clues. And what they found only deepened the puzzle. Why it should follow a simple path. In classical physics, an object path is governed by gravity alone. If nothing else acts on it, its orbit can be plotted with Newton's equations or Einstein's refinements. For interstellar bodies like 3/, this means a hyperbolic trajectory. The eccentricity measured in August 2025 was greater than 1.04. Confirming it was not bound to the sun at perihelion around December 1st, 2025. It should reach maximum speed before slowing forever. That was the expected script. Yet reality broke the script. The Smithsonian Astrophysical Observatory tracked its speed rising at 130,000 miles per hour on August 5th, then dipping slightly below models by August 7th. That's not supposed to happen. Gravity doesn't pause. Something was interfering. Outgassing is the usual suspect, but its distribution was asymmetric. At 2.00 astronomical units, comets often display steady sublimation, but 3/8 pulsed. The The stop-start rhythm, repeating roughly every 1,000 seconds, hinted at processes deeper and stranger than solar heating. Comparisons were inevitable. 2. Boros, discovered in 2019, behaved like a typical comet with smooth acceleration driven by water and carbon monoxide sublimation. 1I/UEMUA, in 2017, defied explanation with non-gravitational acceleration lacking visible outgassing. 3I/AETL sat between these extremes, outgassing like a comet, but deviating in rhythmic patterns like a machine. This hybrid behavior forced astronomers to rethink categories. Was there a third type of interstellar traveler? Neither asteroid nor comet, but something else. The most puzzling evidence came from modeling. Using Marsden's non-gravitational equations, orbital fits worked only if venting occurred at specific longitudes on the nucleus, turning on and off with solar rotation. That implied a rotating body with precise vent structures aligned to produce thrust cycles. But with an estimated rotation period of 17 minutes, 3I/ would be spinning faster than most known comets of its size. A body this large rotating that quickly should fly apart. Yet it hadn't. By early August 2025, astronomers realized 3I/ was defying both orbital mechanics and comet models. It accelerated when it should have coasted, slowed when gravity demanded speed, and spun in rhythms that didn't make sense for a fragile ice ball. To decode the mystery, scientists shifted from orbital data to chemistry. What if the answers weren't in its motion alone, but in the molecules escaping from its surface? That's where the story of 3/A became even stranger. Evidence from spectra and coma activity. The James Webb Space Telescope turned its infrared iTerigim toward 3E/ADLS on August 15, 2025. The data stunned analysts. Instead of a water-dominated spectrum like most comets, the object showed an unprecedented CO2 to H2O ratio. In fact, the amount of carbon dioxide was the highest ever measured in a comet, dwarfing even 2I/Borisov's 2019 readings. Alongside it, Webb detected traces of formaldehyde, cyanide compounds, and even nickel signatures. This was a chemical cocktail unseen in our solar system. Back on Earth, the Very Large Telescope in Chile confirmed activity at 3.5 astronomical units, far earlier than most comets ignite. Normally, sublimation of water drives activity closer in, but here carbon dioxide venting dominated. The tail lengthened to nearly 600,000 kilometers, while brightness pulses match the 17-minute cycle observed in its orbital anomalies. The chemical evidence aligned with the motion. Periodic outbursts of carbon dioxide jets strong enough to alter speed and trajectory, but in bizarrely regular intervals. The chemical fingerprints raised questions about origin. To form with such high CO2, 3I/AETL must have condensed in the carbon dioxide ice line of a protoplanetary disk. That region lies much colder and farther from star than where water ice normally dominates. This suggested a parent star system with conditions very different from our sun's. Computer models traced possible birthplaces to the galactic thick disk over 7 billion years ago, when the Milky Way was chemically young and volatile rich. Yet the preservation of such fragile molecules over billions of years was baffling. Cosmic rays and stellar heating should have destroyed carbonyl sulfide and formaldehyde long ago. Their survival implied shielding mechanisms, perhaps deep layering or unknown chemical stabilization. If true, 3/ wasn't just a comet. It was a molecular vault carrying a frozen record of galactic chemistry predating Earth by 3 billion years. And that vault wasn't quiet. It was erupting, accelerating, and slowing in defiance of expectations. By mid-August, the story had shifted from orbital oddities to chemical impossibilities. 3I/ATLAS carried more carbon dioxide than any comet known, pulsed with 17-minute eruptions, and preserved molecules older than our solar system. Its chemistry explained some of its motion, but not all. The deeper mystery remained. Why was it so regular, so clock-like, and so alien in composition? The answers would demand not just better telescopes, but a complete rethinking of how interstellar objects are born and evolve. The age and origin puzzle. When NASA released refined orbital simulations on August 22, 2025, they carried an astonishing conclusion. 3I/a may be older than the Earth itself. Its trajectory traced backwards suggested a likely origin in the galactic thick disk, a stellar population more than 7 billion years old. That means this comet predates our 4.5 billion-year solar system by nearly 3 billion years. To astronomers, this was like finding a fossil from a vanished era of the galaxy drifting intact into our neighborhood. The thick disk of the Milky Way, identified by surveys in the 1980s, is a region filled with ancient stars, low metallicity, and relic conditions. Stars there rotate around the galaxy more slowly, completing an orbit in about 200 million years. If 3/a truly originated in this population, it means the comet has traveled through at least 30 complete galactic orbits, enduring passages through spiral arms, stellar clusters, and even encounters with giant molecular clouds. Yet its volatile ices, H2O, CO2, and organics remain preserved. Preservation over such timescales was the next shock. Cosmic ray bombardment across 7 billion years should have destroyed fragile molecules like formaldehyde and carbonyl sulfide. Thermal heating during stellar flybys should have stripped away volatiles. Yet spectroscopy in August 2025 revealed intact organics and highly active CO2 venting. This implied either exceptional shielding, layers of insulating dust meters thick, or unknown chemical processes maintaining molecular stability across epochs. If confirmed, 3I/a would force a revision of material science at interstellar scales. The thermal history posed more puzzles. Models predict that comets lose volatiles after multiple star passes. Yet 3/ erupted dramatically near 2.5 astronomical units, as if untouched. Scientists from the University of Michigan, led by Luis Salazar Manzano, noted unusual carbon chain depletion. Far fewer C2 and C3 molecules than any comet ever studied. This didn't match either young or old models. Perhaps 3I/ATL formed in a cold CO2-rich ice line. Or perhaps it had been altered during interstellar travel by conditions never encountered in our solar system. By late August, it was clear 3/a was a relic from the dawn of the galaxy, billions of years older than Earth. But its very discovery exposed a flaw. For weeks, it had slipped past the eyes of our detection systems and classified as a simple asteroid. If a comet this important almost went unnoticed, how many others had we already lost to the noise? The mystery of 3/a wasn't just about chemistry. It was about how blind our machines had become. Automated detection and classification failures. The earliest record of 32/Atlas came not as a comet, but as asteroid designation, a 1PL3Z log by the Atlas Survey in Chile on July 1, 2025. The software treated its odd signatures, chemical, spectral, and thermal, as noise. Machine learning systems trained on millions of known asteroids filtered out anomalies, dismissing what was truly unique. Only days later, on July 3rd, human analysts reviewing orbital mechanics flagged the hyperbolic eccentricity of greater than 1.04, forcing a reclassification as an interstellar object. This wasn't the first time. In 2017, 1/Oumuamua was flagged as asteroid /2017 U1, only later retagged after non-gravitational acceleration appeared. In 2019, 2B/Orosoft was correctly identified quickly because of its bright coma, but only due to its obvious activity. In the case of 32/ALS, the system hesitated. It looked active, but its chemistry didn't match. Without human expertise in spectroscopy and orbital dynamics, it might have been written off entirely. The danger was clear. AI filters have blind spots. This dependence on algorithms has consequences. Programs like Catalina Sky Survey, LINEAR, and NEOWISE all rely on machine classification. Their training data comes almost entirely from solar system objects. Asteroids, comets, Trojans. When something truly alien arrives, it doesn't fit the categories. It risks being discarded. 3I/8TLAS prove that exotic physics and chemistry can masquerade as instrumental error. The lesson was sobering. Without humans in the loop, we could miss the rarest and most important discoveries. The crisis reignited debate over future observatories. The Vera Rubin Observatory, scheduled for operations in 2026, will image the sky every few nights. It promises broader detection, but it too depends on classification models. Space-based proposals like NEO-Surveyor designed to detect asteroid heat signatures might fare better. Yet, even these missions are optimized for near-Earth threats, not alien visitors. 32/ALS revealed the gap. Our systems are not tuned for anomalies. The discovery was almost luck, and luck won't be enough next time. The near miss in detection underscored the fragility of our search systems. If 3/A had slipped away, humanity would have lost the 7-billion-year fossil of galactic history. And now, as scientists scramble to explain its twitching orbit and exotic chemistry, the challenge shifted from discovery to explanation. Why was it accelerating and slowing in clock-like rhythms? To answer, researchers turned to advanced orbital models, running equations day and night to see if comet physics could explain the impossible dance. Modeling the perturbations.